What we're working on is the definitions of these simple words. Velocity. Be careful of the word velocity because yeah, and direction. You need to account for the fact that it is a vector, so it is a change in displacement. It's the easiest way to put it. You can say a change in speed and direction, but it has some connotations which can get messy. Right. You could, but when you think about it, when we talk about distances, it tends to mean the scalar, which means the total motion, whereas the displacement is the distance in a direction from your starting point to your ending point. So if I had a semicircular path, the distance will be that, while the displacement covers a straight line. Yes, it will. Yep. Yep, exactly. Sorry, Josh. Yep. The next one was vector. A vector, Tom, how did you define vector quickly? Yeah, a result, measurement is a better word. Yep. Yep. Now the words we actually use. Yes. The answer is yes. It's not exactly right. You can use any, if you know higher physics from year 4 at university and you can apply it to it, you can do it. Okay.
Like if you get a geometry question in 2-unit maths, you can use circle geometry to solve it. Sometimes the answer is like the circle geometry is right there. If you can't do it in 2 units, just use properties.
Okay, next one was acceleration, wasn't it? Time rate of change of velocity is a really exact answer. The next one was electron.
With a negative charge and an element that defines an atom. Oh no, and it defines an atom along its break.
Now understand, guys, that really is a high school definition. When you go into the university, there's a more complex one, of course. And the last one is rest. So, Riley Anderson, what would you say rest was? Okay, now this is where it gets a little bit complex. Its velocity is 0 compared to? Yep. Really, really important, guys, that you remember that according to Einstein, that any frame is as good as any other, and while we would consider ourselves at rest because our frame is naturally the Earth, if you're on the moon, we're not at rest. So at rest has been referenced to something. I've got 2 hands up. Tom.
Well, this is
Jack, I should say.
Riley showed me. Basically, they got a generator.
Yep.
Which you have to use kinetic energy. But you know how when you throw it, when a cat drops, it always lands on its feet? Yeah. But when a piece of buttered toast drops, it always lands on the buttered side?
Yes.
You strap a piece of buttered toast
to a cat.
And then strap it to the generator.
I've heard that.
Infinite energy.
Yes, it's an old joke, that one, but yeah. Right.
How close would we be going to count in a reference to the center of the universe?
What is the centre of the universe? And how fast is it moving? There isn't a place there is actually not a place you could name as an absolute reference frame. That's what Einstein said. You can't pick a point and say this is the point which is the absolute zero of everything. Pardon? Well, our galaxy, if we compare the Earth to the middle of the galaxy, it becomes really complex working it all out. It's very messy because you've got the rotation of the sun about the centre of the galaxy, you've got our rotation around the sun, there's lots of stuff in it. Yeah.
I don't think this is the exact joke. You the one where like a man goes to the fifth floor and he observes that when he drops the cat, it rotates 2 times the length. Then he goes up to the 7th floor and he observes that the cat rotates 3 times the length. Lands on the feet. Then he goes up to the 6th floor and he kills the cat. Oh yeah, goodness. Because it does 3 rotations from the 7th and 2 rotations from the 5th, and then he would move to the 6th.
Strangely, I was reading a study to do with cat Thank you guys, because we need to move on. I was actually reading a study about cat injuries and height from which they fall based upon vet records in America. And they discovered that, you know, there are a couple of floors where the cat tends to survive okay. Then there's a number of floors where there's critical injuries. And then there's a height from which they survive again. And then there's critical injuries. And they were working out what is about cat falling, which allowed the cat between, say, floors, you know, 5 and 9 to typically survive where they didn't between 2 and 5. And so there is actually studies on this stuff. So, thanks, Riley.
I was going to ask quickly, Simon. Question 3, it says use 3 to 6 experiments. So that's fine, 3 to 6. But in the rubric it says to get full marks, you need to do 4 to 6. And like 6 experiments like that, I've got 4 experiments so far, and that's 2 pages.
Yeah, the reason I put 3 to 6 on it was very simple. I wanted to give a guide as to what the minimum acceptable number were. That's why I put 3 as a bottom number.
So you really need 6.
Yeah.
Do you have any ideas? Because like Kirchhoff junction rules, is that one that we can use?
Yeah.
Because like, but there was no experiment that I found. I just found that like all the sum of currents flowing into a
Yeah,
junction.
Kirchhoff did you should look up Kirchhoff and his experiments. He had lots of experiments on it.
Because the 2 ones that I've done I've done 2 on superconductivity.
Yep.
I've done one on Faraday electromagnetic induction, and I did one on, you know that thing I told you. You know that experiment I told you about, the one that's a conductor and an insulator.
Yep.
Did one on that.
That's 5 you got.
No, I got 4.
4.
2 superconductors, made for Faraday, and then.
There are way more than 2 superconductor experiments out there.
Well, I just thought that I was kind of exploiting it.
No, like, you know, multiple in the same subject area. That's okay. Not a problem.
But shouldn't the max be out 4?
I think that's a bit excessive. 6 experiments. Like, because you don't like us to write too much, but I find that it's pretty hard to get full marks and not write a lot. That makes sense. Like, you can either not write in depth and write succinct
Yep.
stuff.
Yep. I can understand what you're saying. But I can't really.
Yes,
We do that tomorrow. Okay, everyone. Shh. We're going to focus on what we need to focus on today, which is, if you look at the syllabus, and we're up to, we've essentially, we've gone down to describe the force acting on a charge moving through a magnetic field. No, we're not having private conversations. It's very simple. Thank you. So, that was that F equals QVB sine theta, and those sheets asked to do. And I'll give you, I'll make sure for the next lesson you get the answer page for that so you can do them. The next thing we need to move on to finish basically is outline Thomson's experiment, and then the thing about the electron gun and deflector plates and the fluorescent screen in conventional TVs, they call it, and oscilloscope. So that's this afternoon's thing, yeah. Yeah, can go.
Same we're doing on.
Excuse me, hang on.
Same we're doing Thompson's third experiment.
We can do any of his three. Any of them. Now,
Where you going, Craig? So it's never before. Yeah, Mama's back.
for people who are very keen on knowing the history of this and the ins and out of it, there is a link to this, which is a chapter out of a science history book, and it outlines a lot of the stuff that Thomson went through in great detail, in way more detail than you guys need to know about. Okay, but it is interesting. It talks about his reluctance to use the term electron in his work and why, and his interactions with other scientists and what led him to develop the gear he did and all that sort of thing. So it's an in-depth look at it, which has some interest. Yep. Okay. You'll notice that this particular sheet only refers to one of J J Thomson's main experiments, and that's okay. The syllabus itself talks about J J Thomson's experiment, as I've said before. He in fact conducted a number of variations on this experiment, and when they ask you about Thomson's experiment in the HSC, you can talk about any of them. If you want to be really complete, you could talk about all three, but just talk about one of them will do. Now,
How do they vary?
well, one of them he just used electric plate. One he used just a magnetic field through it. Another he used a combination. He did some other stuff, and he used different styles and setups.
What was he doing? What did he do?
Well, if you have a look, and we'll explain it on the yeah.
Can we use this in our assignment?
You can use any source in the assignment you like. What you can see here is a diagram or representation of what a lot of people would regard as his classic experiment, I suppose. And if you're asked to explain his experiment, drawing that would be a particularly useful type of diagram. Now you'll notice something here. First of all, you have a cathode. What is a cathode a source of, Marnie? What is a cathode a source of? There's the cathode at the end of the evacuated tube. So what's the cathode a source of? No, not what's connected to it. What does it give us? It gives off the stream of electrons, or what he called cathode rays. Because when he did this, he did not know what they were particularly. He had some ideas, but he didn't actually know what they were. And in front of it, you have a positively charged plate called an anode. And what is its function in this thing? Because you want them to be up here. It's a positive charge. What will it do to the... yeah, it provides a potential, doesn't it? It accelerates the electrons which are released from the cathode towards the anode, and the anode itself had a hole in it.
Is that why, like, on old TVs, the CRT TVs require like 10,000 volts or something? Because they
Yeah, that's the next part of the syllabus, next dot point. It is. That's what it does. Because you have an electric field there, charged particles will be accelerated by the electric fields, but if you didn't have the anode there, it wouldn't accelerate it. So it is the... Because you need high energy travelling electrons to do anything with them. That's what he wanted. Because if that wasn't there, they would not be ejected by the cathode. Okay? Yeah, Riley.
But don't we do it so they come from the anode to the cathode?
No. Cathode rays always go from the cathode to the anode, but for us, a conventional current is in the opposite direction. Yeah, the current for us and the electric field are that way, but the electrons, the cathode rays, go that way. Okay? Shh, no.
So, is the electromagnets are on that plane same, like, won't it bend the light that way, like towards in or
Careful.
forward?
Okay. So what's happening here, guys? You've got a source of electrons. They're accelerated by the anode and focused. There's a slit in there, so they go through that. There's another focus there. You can see that little disc there was just for focusing it, so you get a nice narrow beam, which you could work with. And then you'll notice it goes past electromagnets and another set of electric plates. Now they're called deflection plates. Right, you'll notice that the magnets are at 90 degrees to the electromagnets, right? Now the reason for this is very, very simple. If you think about our equation with Q V B sine theta, right? F is Q V B sine theta. You can use a right-hand rule, Fleming's rule if you like, to work out the direction that they're going to bend. And if you look at it, if, so B in this case is that way, I is that way, so they're going to get bent.
Force is downwards.
Yep.
But how come they're bending up there?
Well, in this case, right, let's go slowly with this without the talk. Okay.
But if it's flying,
Hold it. Well, thank you. In this diagram, when I do it, I get that pushing the, deflecting the beams down. But they will only work when there's a current flowing through the electromagnets. With the deflector plates, that's a positive plate. Which way will the cathode ray be going? That's it. No, you don't need hands to work it out. If that's a negative beam of particles and that's a positive plate, they're going to be bent up.
so it's not the right angle.
So
So the force
hang on. Guys, if you're concentrating, not hard to see. Cathode rays, we know today they're negatively charged. They knew that then, and we know they're electrons. If that's a positive plate up there, you've got a beam in them coming, and that positive plate is on, it will deflect them upwards like the picture shows, correct? No, it won't. You'll experience a force upwards.
So if the field's going positive, negative, positive, sort of that, it can't like that. So
Yeah, so I think what he's saying is even though there's electric plates and those electrons are going to be pulled up, because there's electromagnets and a flow of electron charged particles, shouldn't there be a force acting on it?
Right.
Yeah.
Try again. As these electrons are passing that plate, remember, they're electromagnets. If they're not switched on,
Oh, so why are they
there's
there?
nothing. I said if they're not. So in this diagram, they're showing it as though it was not switched on and it's being deflected upwards.
Okay.
Right. So what you can do is you can measure the angle of deflection there. And by measuring the angle of deflection, and you know the electric field across there because you apply it, you know some stuff about what's going on, you can do some maths about it. Yeah. The other thing you can, but then what you can do, you have two choices. You can switch off those plates and switch on the electromagnets, and it will deflect them down. And then you can measure that angle, and if you know the magnetic field, you can do some other measurements about it. What you can also do to, you can switch them both on simultaneously, and you can adjust them so that the beam ends up being attracted up by the plates but being forced downwards by the magnets because they're at 90 degrees, and the beam just keeps going straight through. Now, well, it'll just go straight through as well. There's no force. Now,
So how come you let the magnets make it bend up or down and not left or right?
because they're the orientation they're at 90. The electric plates are one way, and the electromagnets at 90 degrees. So right, if you use FBI, B will be that way, I is that way. There's a downward force. Okay, so there's a downward force on it. Thank you, Riley. Now, the advantage of doing that, if you switch on your plates and you get a deflection upwards, and then you switch on the electromagnets, turn them on too much, the deflection will downwards. But then what you can do is you can adjust them until you end up with a straight line. Now, what that tells you is the force due to the magnets is equal to the force due to the electric field. And once you know that, then you can start doing some maths around it.
The electric field plates are magnets and the electromagnets are
No, they provide an electric field for field plates, and they provide a magnetic field. So that's right. So if it's only the electric field is operating, it gets deflected up. If only the magnets are electromagnets are operating, it gets deflected down. And if you turn them on in the right with the right strength for each, then you can get it so it goes straight in the middle. And when it's straight in the middle, you know the force applied to that beam by the magnetic field must be equal to the force applied to the beam by the electric field. And then you can do some very clever maths. Now, on the sheet I've given you, I'll just get rid of those things. Oh. There is a slight difficulty in using this sheet for you. No, it's actually not too advanced for you. But if you read it, it talks about how Thomson came to his conclusion. And I'll read it out. In this coordinate system, electrons enter the region between the plates with an unknown velocity v in the x direction. In order to determine this velocity, electric and magnetic fields are both applied and each give rise to a force on the electron. These forces are in the y direction, up and down. The electric force, Fe, equals, now they use the terminology little e, big E. Little e being the charge on the electron. So for us, that equation there should read F equals, no, EQ, because we use the symbol Q for charge, or QE. We actually know that formula, it's just written in a different way. Okay, so their little e there is the same as the Q that we use in our formula. Right? Now, yes, where E is the magnitude of the electric field and the magnetic force is FH. Now notice H, in this case, is his symbol for the magnetic field, which would be the B. So where is written FH equals EVH, we can rewrite that FB equals E is charge. That symbol there is our V, that E is a Q, and that H is a B. Right. I'll do it slowly. This equation here, he has written FH equals minus EVH, right? Now he's used symbols in different ways. So where he has H, we have B. Where we had a funny V, we have V, and E is our Q. So remember we use the formula F equals QVB and a sine theta. That is actually that. It's exactly the same formula, just with different symbols. Yep. That's just to show you that when we have Q, if we're dealing with negative things, we put a minus in it. If we're dealing with positive things, we put positive in it. He's just assuming that it's negative to start with.
So the electron is negative.
Because electron's negative. So, I don't know if it will change. Now, guys, if you notice, once you realise that we're actually dealing with the formulas we use, the paper starts to make simple sense for us. But I needed to point that out because students are often confused when different authors use different symbols for the same stuff, and that happens all the time. All right. So what we find is FB equals QVB, as we know, and it talks about that. If these forces balance, there'll be no deflection of the electrons in the y direction. In other words, they go straight through, like it said to you. All the electrons' motion will be along the x direction, which is the initial direction they enter the field. They go straight ahead. That's what he's saying in normal language. And it's good to learn how to decode this sort of writing. If the force is balanced, then the total force of the electrons will be zero. That's the force due to the electric field plus the force due to the magnetic field is zero. Or, he's written it that way, but if we write it, we would rewrite that formula as EQ plus QVB equals zero. That's how we would write it. So Thomson actually took that idea and then he could start doing some substitutions. Now, he knew that the velocity can be determined as the strength of the electric field over the strength of the magnetic field. Then he turned the magnetic field off so that the force was due to the electric field. Since the force is non-zero, if the charge carriers can be deflected by the force, this provides evidence for there being fundamental particles, etc. And you can know they would have a well-defined charge and a well-defined mass. And he talks about the formula that you use. Now, note something that is said which is very important here, and this has happened in the HSC before. This statement here, this problem is exactly the same as that of a projectile in a gravitational field.
Oh, is that why some of the questions in the HSC are related to both this
They fire an electron
into
an electric field which exerts a constant acceleration downwards on it. It follows a projectile path and you use your projectile problems to solve it. Equations to solve it. Yeah.
So is that an electron in a magnetic or an electric field?
Constant electromagnetic field, yep.
And you can work out how far it's going to. But
Mhm.
it's not like it has to be in between plates, because obviously if it's just by
Yes.
the plates, it's
Yes.
just going to bend down.
That's right. Right. And so we can use the projectile motion using X and Y coordinates independently to do some mathematics about it. Now, you're not required to be able to reproduce the mathematics, which is all there for you. But he came up with a charge to mass ratio. He's able to work out, doing this stuff, that there was eliminating all the other things, that there's a charge and a mass ratio, and it has a number associated with it, which is written there. The thing about it is that it meant something. It meant it had an alternative. This thing either had incredibly small mass and was part of atoms, or alternatively, it might have a larger mass in comparison to a smaller, a different charge. That's coulombs per kilogram. Now you notice that's a very, very big number, 1.75 times 10 to the 11. So if a mass of electron is very small, an awful lot of them would gather up to give you a very large, a kilogram of them will give you an awful lot of charge. So you had a choice. Was it a large mass with a certain charge associated? Very small mass. Now he took a gut instinct and he said he believed that it was in fact about 1/1800th the mass of what they thought atoms were, and he believed from other evidence around that it was probably part of an atom, a fundamental particle. He's pretty good actually. He got within about 5 to 10% from memory in the region of what he wanted. Here. Thomson found that for cathode ray particles, the charge to mass had a ratio was in the order of 10 to the 11 coulombs per kilogram. His order of magnitude was correct. Most importantly, he found that the value was not affected by having different gas in the tube or by varying the metal of the electrodes. So he concluded that his particles were not associated with a particular element. They had to be something that belonged to everything, essentially. So he thought they were everywhere. He's aware that QM had been estimated for various atoms many years previously using data from electrolysis. Hydrogen, the lightest element, gave a figure of 10 to the 8, smaller by a factor of order 10 to the 3. Clearly the rays did not consist of charged atoms. Either their mass was much smaller than the hydrogen atom, or the charge they carried was very much bigger. The mass of a hydrogen atom was known. Thomson suspected the charge in his U particle was in fact equal to 1 electron, that is to Stoney's fundamental unit of charge, E. The same charge is carried by a hydrogen atom in electrolysis. So making that assumption, it meant that hydrogen atoms had to be 1,800 times heavier than his electron. Yep.
So he had a range of different elements which would have been lost gases. And then did he figure out like how he used like ratios with how much it fed to detect how many electrons there were?
No. It was just simply interested in the charge on the things that would be, the charge and mass of these things are being bent. He did not have the equipment or the understanding to test his hypothesis. He put forward this idea. This thing was not solved until the 1950s when a fellow called Robert Millikan came along and did a fundamental set of experiments, which he got a Nobel Prize for, which showed the charge on electrons. It used to be part of the syllabus, but they got rid of it. Don't ask me why. It was actually a good thing to look at. Think about Millikan, and I've got on YouTube, there is a video about him. The thing about Millikan's work is that it was painstaking. What he did, he designed experiments several times, but he ended up with a special capsule, and he'd spray oil droplets in which he charged. He made sure they weren't interfered with anything, and they would drop, because they're aerosols, they'd drop slowly down. And he had a little window, and had some marks on it. And he timed how long it took for these little drops to go down between the two marks to find out their mass from their gravitational acceleration, right? Then what he'd do is he'd switch on electric field and time how long it took, because the electric field is a reverse direction to the gravitational force, and he knew the size of the field. He'd time how long it took to go back up between the two marks. Then he'd switch off that. He'd time it to going down again. Then he'd switch on. He'd go up again. Yes, it's that one. Now, this particular bloke did the same measurements for a couple of years, and he took something in the region of 10,000 measurements before he started doing his calculations and work things out. There's great patience, but also it's interesting that he would look at results, and at times he'd just simply say, this set of results are not right, I'm not going to use them in my final results, because he had a gut feeling about what he was looking for. Okay. What we do have, though, is Thomson did come up with a model, because he said, I've got these things which I agree with the name electrons in the end. They're 1,800 times smaller than an atom, how they fit into things. And we came up with the Thomson plum pudding model of the atom, which we'll go and have a quick